Hello, can you see me now?
Yes, we can see you.
Hello.
So happy to see you.
Right. It's a great honour to receive the Henri Poincaré Prize. I'm grateful to Vladimir Bazhanov, Murray Batchelor, and Reinald Quisbell for nominating. They are three of the many advisors and colleagues I've had over the years. The first were the teachers at Bancroft School in Essex, England in the 1960s, 50s. I'd always been interested in mathematics. I can remember my father showing me how to calculate square roots by a process much like long division. From there, I went on to Cambridge, and from there to the Australian National University and to the Massachusetts Institute of Technology. They were two very important years for me. I worked with Elliot Lee, and he introduced me to the ice-type models. And I was able to generalize some of his work, and from there to and do some more work before my wife and I left in 1970 for 5 months in England prior to taking the ship back to Australia. Towards the end of that stay in England, I realised that I picked up a paper that I'd written at MIT, trying to generalise the 6 vertex models to completely, as far as possible, to an inhomogeneous square lattice. And I observed in this paper that there were 2 properties that stood out. The first was the eigenvectors of the row-to-row transfer matrices were independent of a parameter, now known as the spectral variable. That meant that all matrices commuted. The second property was that one could write the final result, the beta equation, as a functional relation between the transfer matrix, considered as a function of the spectral variable, and an associated matrix, Q. Further, one could normalise the matrices so that they were entire functions of the spectral variable. Then the functional relations determined all the eigenvalues and hence gave me the partition function of the model. This led me to wonder whether this could be generalised to the 8-vertex model, which Elliot had introduced me to. The answer turned out to be yes. Actually, the commutation property had already been established by Bill Sutherland, and I was unaware of Bill's very recent work. So I began working on this sum while still in England and finished it in the ship's library on our way to Melbourne, polluting the air with my pipe smoke as I did. It was more or less complete when we arrived in Melbourne before Christmas 1970. The proof of both the commutation property and the needed functional relation involved local relations between the Boltzmann weights of the model. The one for the first property, the commutation relation, came to be known as the Yang-Baxter relation. My calculation relied heavily on using the elliptic functions of Jacobi. I recall that one writer commented that it was 19th century mathematics. I was happy with having used 19th century mathematics in the 20th century. I've done other things in the following 50 years, notably inventing infinite dimensional corner transfer matrices. Even for models that defy exact solution, they can provide a powerful tool for series expansions or numerical calculations. However, It was this work, immediately following my collaboration with Elliot Lee, that set me squarely in the field of exactly solvable models. I note that this session includes early career researchers. Maybe that's heartening. Maybe I've got another 50 years to go. I thank IAMP again for the great honour of the Poincaré Prize. Thank you. I'm afraid I can't hear you still.
Thank you very much. I'm so happy this worked out. Now we can continue, as you said, with the next session. The Early Career Award winner will speak next. Let's thank Rodney Baxter once more. And here is Laszlo Erdős to introduce Amol Aggarwal.
Thanks very much, Bruno. So I'm the chairman for this morning's session. It's a great pleasure for me to introduce Amol Aggarwal, who is the 2021 winner of the Early Career Award, sponsored by Springer. We already heard his laudatio from Fabio Toninelli on Monday, but let me just say a few words who were not there about Amol. So he did his undergraduate at MIT. He was an extremely successful, very young mathematician. He already had 4 published papers before he even started his PhD. Then he finished his PhD in 2020 at Harvard under the guidance of Alexei Borodin officially, but he also worked with Horn-Sen Yao. Then he immediately became a Clay Fellow and was appointed to Columbia, where currently he's an assistant professor. His work is very broad. He's well known for both for his probabilistic and combinatorial achievements. Among others, he wrote in very influential papers on the ICE model, on the current fluctuation of the the asymmetric symmetric exclusion problem, and most importantly, probably the problem that he will talk about today, is about the grand universality of the Lausanne-Stiling model. So it's a great pleasure to have Amol here, please, for his talk. And so before you can start your talk, this is a medal from IAMP for every speaker.
Thank you.
So thanks very much for your talk.
Thank you. So thank you very much for the very flattering introduction. It's an honor to be speaking here, and it's also an honor to be following the words of Rodney Baxter, whose work had influenced my studies and my work throughout my short career so far. Anyway, so I'll be talking about universality results in random Lossenschellings. So let me begin by describing the main model of this talk, which is a Lossenschelling. So they'll take place on the triangular lattice, which is depicted to the left in this figure over here. As you can see, all of its faces are equilateral triangles, and we'll call 2 faces adjacent if they share an edge. So pairs of adjacent faces are called tiles or lozenges or dimers. These 3 words mean exactly the same thing, and I'll use them interchangeably. And as you can see, there are 3 possible orientations for how these lozenges might look, and they're shown to the right. Yeah, they're shown. Let's see, can I? Oh, yeah, okay, they're shown to the right over here. And there are 3 orientations of these lozenges depending on along which edge these 2 faces meet. The top one is, you might view it as sort of pointing vertically, and the middle and bottom ones point horizontally. You can view the middle one as pointing to the left, and the bottom one as pointing to the right. So what we'll be doing in this talk is we'll be considering tilings of subdomains of this triangle lattice using these 3 different types of lozenges. Okay, so I've given just one quick example on the top middle, where you can see a hexagon of side length 2, and I've drawn a Lossenschelling of it. This is one of several types of lozenge tilings, just to give you an idea of how it might look like. So a useful thing to keep in mind is that lozenge tilings can also be interpreted as step surfaces or as height functions. So to illustrate that, I've taken a hexagon of side length around 25 or 30 on the left side here. So as always, there are 3 types of lozenges in this picture, and they're shaded in 3 different colors, all different hues of gold. So I mean, there's a dark gold, a light gold, and a medium type of gold. The vertical lozenge here is the medium gold, and the 2 horizontal lozenges are light gold and dark gold respectively. So I hope, in addition to seeing a lozenge tiling, what you might see is a step surface. Namely, you can imagine this hexagon being a big room, and the middle of the hexagon being the corner of the room, and then you pack a bunch of boxes into the corner of the room, a bunch of gold boxes into the corner of the room. And what you see is sort of zoomed out is the surface created by these boxes. So this is an example of how you can create a step surface from a lozenge tiling. A height function is simply defined from the step surface by indicating how high the surface is, the height of the surface is at any given vertex. So to just give a quick example of that, you might look on the right side, here, where I just have taken a hexagon of side length 1 and I've drawn a lozenge tiling of it, but I hope you also see a box. And in this box, if you say pin the height function to be h at the bottom left corner, then you can view these 3 vertices as existing on the bottom layer of the box, and these 4 vertices existing on the top layer of the box. And this tells you that if the bottom height function, if the height at this vertex is h, then the height at these 3 vertices had also better be h. They all lie in the same layer. And likewise, they'd better be h plus 1. They lie in the above layer, the top of the box over here. Okay, so that's just an example of how a height function looks on this very small hexagon. And you can likewise consider this larger hexagon, where I've taken a lozenge tiling of it, but you can also view it as a packing of boxes of the type shown on the right into the corner of the room, and then you can fill in the height function in the sort of straightforward way that you would imagine pictorially. Okay, so this is all to say that there is, for any lozenge tiling, you can view it as a step surface or a height function. You can also go in the reverse direction, namely, given a height function, you can turn it into a lozenge tiling. I'll just quickly describe that, although it won't be central in this talk. So to describe that, you fix some domain R that you're going to tile it, and as I just mentioned, associated with this tiling, there's a height function. So if I restrict that height function to the boundary of the domain, I get some function on the boundary of the domain, which I'll call a boundary height function. So over in this picture, in the middle picture, the boundary height function has zeros along the bottom and the left boundary, and then it goes up linearly, and then it stays constant, and then it goes down linearly as I cycle around the hexagon. So it's not so hard to convince yourself that this boundary height function, it actually doesn't depend on the tiling. As I said, you take the tiling, and then you restrict to you look at the associated height function, and you restrict to the boundary, but it actually doesn't depend on the tiling itself. It only depends on the domain. And this is, so the statement then of the bijection is that any height function on your domain with this specific boundary data corresponds bijectively to a tiling of R. So as I said before, you can go back and forth between height functions and tilings. I might do that in what follows a little bit, although it won't be super central. Okay. So in this talk, we'll be considering uniformly random tilings of very large domains, or equivalently, you might view it as the dimer model on large subdomains of the hexagonal lattice. And the basic question we'll be interested in is, how do uniformly random tilings of very large domains behave? So the main focus of this talk will be on local behaviors of these tilings, but let me just take 2 slides to talk about the macroscopic or the global behaviors. And the first, one of the fundamental results in this direction concerns the law of large numbers, or the so-called limit shape that was proven by Konkinen Prop in 2000. So the statement, somewhat informally, is the following: if you take a very large domain, a general, more or less arbitrary large domain, then this, as I mentioned previously, you can take a random lozenge tiling of this very large domain, and associated with this lozenge tiling is a height function or a surface. And the statement is that this surface converges to a limiting surface, or a limit shape. I have not given you, there's a formula for the limit shape. It's given by the minimizer of a certain variational principle, which I've not written down here, but you can characterize it in such a way. And what's important to observe about such limit shapes is that they strongly depend on the geometry of the domain you're interested in. So although you might imagine the domain having perimeter n and the area of the domain being n squared, the shape of the domain is heavily influences the behavior of the model inside the domain. So just to illustrate that, I've given sort of 5 examples of different domains. I have a hexagon, an octagon, some sort of strange S-shaped polygon, a triangle whose edges are somewhat jagged if you look closely enough, and a parallelogram. And the behavior of the model of the random Lawson-Schelling in each of these domains looks drastically different. Maybe the two most different ones are the last two. As you can see in the 5th one, the parallelogram. The whole thing looks completely frozen. They're only vertically pointing lozenges. And this is fairly straightforward to convince yourself of because there's only one tiling of that parallelogram. It's going to be the one where there are only green vertical lozenges. Whereas this triangle here, the whole thing looks somewhat random. You see lozenges of all types occupying the region. So so these limit shapes are very strongly dependent on the geometry of the domain, and they can be very inhomogeneous in the sense that the densities of tiles can strongly differ in different parts of the domain. This is made fairly clear from looking at the hexagon on the left side here, where the corners of the hexagons are sort of saturated with all tiles of the same type. For example, the top left corner is only saturated with these yellow lozenges, which are pointing to the right. Whereas if you look in the middle, you'll see lozenges of all different types. Okay, so this is all talking about sort of the limit shape. One might also ask about fluctuations, which won't be a topic of this talk, but I would go amiss without mentioning a word on it. So the conjecture, which was due to Kenyon Okunkova around 15 years ago by this point, is that the fluctuations around this limit shape of this step surface converge to the Gaussian free field. This remains open, but it's proven by many people, too many to list in this slide, on various families of special domains. So, okay. I'll talk a little bit more about macroscopic features before going into the local ones. So depending on the boundary, on the shape of the boundary, the limit shape can exhibit various different behaviors, and 2 of these behaviors are frozen and liquid regions. So frozen region is sort of the one shown in the bottom right here. You can look near the corner, but not exactly on the corner, and you'll see that you'll see all lozenges of the same exact type. They're all aligned with each other. So in such a case, if you only see lozenges of one type, these are often referred to as frozen regions or facets. And you can view them as induced by the boundary conditions. Namely, these lozenges here, the ones that are pointing to the right, are the ones that sort of fit nicely into the corner of the domain of this hexagon here. So, these are the ones that sort of want to be fitting into that corner, and this sort of favoritism toward these red tiles propagates macroscopically into the interior of the domain, creating a facet. Now, if I look inside, if I look closer inside the domain, I see lozenges of all different types, each appearing with positive proportion. And we call such regions liquid regions or rough regions of the surface. And there is a phase transition from rough to liquid, given by this black inscribed circle, which would often refer to as the Arctic boundary that separates frozen regions from liquid regions. Okay, so these are all properties of macroscopic properties of these lozenge tilings. So again, the focus of this talk will be on more local behaviors or local statistics of these random tilings. So by zooming into different points of the domain, you will see different limiting statistics. So for example, maybe one point you might want to zoom into is a generic point, say in the liquid region. I won't, is a generic point in the liquid region, which is shown in this green here. So I've just taken a point in the interior of this sort of inscribed circle, where you see lozenges of all different types. These are known as bulk statistics because you're looking in the bulk, sort of a typical point, inside this liquid region. And here you see lozenges of all different types. So this is one point you might consider zooming into. Another point closer to the boundary would be a point on the edge of the facet. So where the facet stops becoming a facet. You can zoom in around this area, and you'll see different limiting statistics. And going closer to the boundary, actually on the boundary, you can look at a point where this Arctic curve, where the circle becomes tangent to the boundary in this blue box here. So near a tangency point, you'll see yet another behavior, another local behavior in the model. So what I'll be interested in is how what sorts of limiting statistics arise, how they depend on the domain, and how they're universal. So yeah, the goal is to understand these limiting statistics and their dependence on the domain, which you can view as consisting in two parts. The first is computing these limiting statistics on a specific domain, so for example for a hexagon, and then to show that these limiting statistics appear universally on very general classes of domains. So yeah, so again, the goal is written over there again. And I will take these 3 points, the same 3 points that I had mentioned on the previous slide, the bulk of the liquid region, the edge of the facet near a tangency location, and I will go through them sort of one by one in the remainder of this talk and explain first, the first bullet point in each of these 3 is telling you what the answer is on a specific domain, what the computation gives on a certain domain. And the second result gives a universality statement saying on what family of domains can you prove these statistics to hold in general. So for the bulk of the liquid region, I will go through this in much more detail in the remaining part of this talk. But in the bulk of the liquid region, it was basically shown by Conkenny and Prop that you see on specific domains, in particular, they were looking on the torus, you see an ergodic translation invariant Gibbs measure, which is somewhat explicit. You can write it in terms of the discrete sine kernel or an incomplete Bessel kernel. So this is for the torus, and then the general statement is that this result appears in the bulk of the liquid region on more or less arbitrary domains. Concerning a near tangency point, it was shown by Johansson and Nordenstam, and also by Okunkov and Reshatikin, both in 2006, that you see a Gaussian unitary ensemble corners process, a GUE corners process, and the somewhat recent statement by myself and Vadim Gorin is that this actually appears at a tangency point on more or less on fairly general domains again. And the final point will be near the edge of the facet. It was shown by Johansson in 2000 in a special, again, so in a special case for a special domain that you see the Airy process or the Airy line ensemble. And in soon forthcoming work with Jiang Huang, we show that this appears for a very wide class of polygonal domains. So I will go through these 3 points in more detail in what follows, and you can maybe quickly, already see that these limiting statistics admit rather close connections to random matrix theory. So I'll comment a bit on that in what follows. Okay, so I'll start with the bulk of the liquid region, sort of the typical point inside the liquid region. So just to set notation, let's consider a domain R, which is a subset of this triangle lattice, and we'll consider a uniformly random tiling of it. So you should view R as very large, and we'll take a random tiling of it. We'll fix some vertex V inside the domain, so maybe you can view it as the center of this, You can view it as the center of this green box here. And you take some order 1 neighborhood of it, say like a 10 by 10 neighborhood of V. So now I've taken a random tiling on my big domain R, and I can restrict this tiling to this order 1 neighborhood of V, and this will give it a random tiling of this order 1 neighborhood. So I can take this, I can alternatively view this as taking the size of the domain to infinity, and then I can follow that up by taking this sort of local neighborhood, this green box, also to infinity, but much more slowly. And I'll get a random tiling on the full plane by sort of taking this green box to exhaust the full plane, but much more slowly than I'm taking the size of the domain to infinity. And the bulk statistics question asks, what is the law of this random tiling? So an immediate observation you might realize is that this green box doesn't actually see the boundary of this domain. I mean, it's well inside the boundary of the domain, but it will still very much feel it. If I go back, you can immediately see that this parallelogram, if I look in the center of this parallelogram and sort of look locally inside of it, you will always see the lozenges pointing up, even though, say, a local neighborhood of the center of this parallelogram doesn't necessarily see the boundary. It doesn't see the boundary of this parallelogram. It will still feel it. The local statistics will still feel it in the sense that it will only see lozenges pointing up. Whereas if I look in this triangle, in the center of this triangle or this hexagon, if I look in the center of them, the local statistics will look much more random, even though, again, this neighborhood can't actually see whether or not the domain is a hexagon or a parallelogram or a triangle. Okay, so going back here. So again, the bulk statistics question asks, what is the law of this random tiling on this neighborhood of my vertex? And this contains all correlation functions of nearly neighboring tiles in this random tiling. So the general prediction in this context is that the limiting measure. So again, we again adopt the viewpoint that you're first taking the size of the domain to infinity, and then you're very slowly taking this local neighborhood to infinity as well. The general prediction is that this measure that you get should satisfy three properties, namely translation invariance, ergodicity, and the Gibbs property. So just to remind you what these properties are, translation invariance means that you're invariant under any shifts of the lattice. Ergodicity means that any attempt to write your measure as a linear combination of translation invariant ones is trivial. And then the Gibbs property, again, since we're looking at loss-in tilings, since when you take this local neighborhood to infinity, you get a loss-in tiling of the full plane. You can't talk about uniformity in general, and therefore you ask for the Gibbs property instead, namely that if you cut out a finite neighborhood, a finite subset of the lattice, and condition on everything outside of that neighborhood, then you're uniform. Then the conditional law is uniform inside of that neighborhood. Okay, so a theorem which goes back to the thesis of Scott Sheffield is that for a given is a characterization of all types of measures satisfying these three properties. Namely, for any proportion st and 1 minus st of tiles, there exists a unique translation invariant Gibbs measure, or ergodic Gibbs measure, mu of st, on tilings of this full plane, with the proportion of vertical tiles being s, right pointing tiles being t, and then the left pointing tiles being 1 minus s minus t. And we'll often say that this measure has slope st, and the reason for the word slope is that the height function associated with this measure, the height function associated with the tiling sampled from this measure is approximately planar, and the slope of this plane is s comma t. So this is all, so there's a theorem that basically tells you how such measure satisfying these three properties looks. But the difficulty is actually showing that your measure satisfies these three properties. So the Gibbs property is somewhat obvious. I mean, it follows more or less because of the fact that it holds in the finite. But the translation invariance and ergodicity is much less obvious, especially for very general domains. And in fact, if I look at more complicated statistical mechanical models, such as the ferroelectric 6-vertex models, these properties can be false. So I mean, you have a natural conjecture for what the limiting Gibbs measure should look like. Namely, these should be given by these mu STs for these local statistics. But I mean, you would still need to prove that. I mean, the statement still requires some work to prove. So I've told you what I've given you a somewhat abstract characterization of these mu STs. I want to tell you somewhat more explicit characterization of them. So to do that, I will first observe that any tiling of any domain is determined by a set X of the locations of the vertical lozenges in the tiling. So in particular, what I mean to say is that if I take this tiling of the hexagon and I just fix all of these dots, the locations of the vertical tiles, then I can fill in the rest of the tiles deterministically. So all I need to do to tell you what this tiling is to fix the locations of these dots. Okay, and the statement there's a characterization of how these what the probability of seeing these dots in given locations is. So it was proven by Okunkov and Reshetikin, again on the case of a special domain, that the probability, if I look at these local statistics under these mu STs, the probability of seeing these centers, these dots at locations x1, y1, x2, y2, although I have to say xm, ym, it's given by a determinant, a fairly explicit determinant. So I'm looking, this is given by an m by m determinant, whose entries are given by this k here. And these k's are explicit, so this k is given by an integral, as shown over here. And the integral is completely explicit except for this c, and this c is in turn explicit in terms of the slope, st. If I give you an st, then I can compute what this c is, and therefore I can compute what this k is. And given this k, I can compute all sorts of, all probabilities of seeing vertical lozenges at various points in my domain. So this description in terms of a determinantal point process for for these vertical lozenges. It's sometimes known as the incomplete Bessel process. It's actually very useful for computing local correlation functions. So for example, you can just use this to say that the probability of seeing two adjacent vertical tiles under this measure, under this translation invariant ergodic Gibbs measure, is s squared minus sine squared pi s over pi squared. And those people who are familiar with random matrix theory know this as a discrete analog of the sine process for Hermitian random matrix local statistics, for local statistics in the GUE model. Okay, so these previous results were for the torus. I mean, they were for the translation invariant Gibbs measures, and how you get those measures, at least a priori, is by taking the random tiling of a torus and letting the torus go to infinity. And now, so I want to state a theorem which is saying that these local statistics, you'll see these local statistics appear in a much more broad setup. So I'll fix basically a very general domain R, so it'll be simply connected and piecewise smooth boundary, and even these can be relaxed. Even these conditions can be relaxed to a great extent. We'll fix some large integer n, and we'll fix some. So you should view this this curly R as a continuum subset, and then the Roman R as a discrete one. So we'll fix some tileable domain R in the triangular lattice. That's scaling down to this continuum R if I divide out by n. I'll fix some continuum point in the continuum domain by v, denoted by v, and then in the discrete, I'll fix some vertex v in this R, which I'll denote by vn, such that if I again scale vn down by v, I get by n, I get the continuum v, and then I'll let m denote some random tiling, some uniformly random tiling of my discrete domain. And the statement is that as n tends to infinity, the local statistics of the tiling around v are given by one of these translation invariant Gibbs measures, where UST, and this ST can actually be made explicit. It's the gradient of the limit shape. So as I recall, there's a limit shape associated with any tiling. So it's given by the gradient of the limit shape at this vertex v. So this result had been predicted by Konkinen prop in 2000, and the dependence. So I mean, these limiting bulk statistics, they involve infinite limiting correlation functions, and they're strongly dependent on the domain, as I said before, and this theorem more or less isolates the dependence on just two parameters, s and t. Okay. So this is all for the bulk statistics. I want to next proceed to near the tangency locations. So we'll fix a point where the Arctic boundary is tangent to, say, a horizontal side of the domain, any side of the domain, but let's just say horizontal to fix the idea. So we'll take this point here, for example, and we'll consider the scaling will be slightly different here. The correct scaling will be to consider an order n to the 1/2 by order 1 neighborhood. So I'll go n to the 1/2 in the parallel direction to the side. So in the horizontal direction, I'll go n to the 1/2, and the vertical direction, I'll go order 1. And I'll zoom in and I'll ask myself how the tiling looks in this region. So what you can quickly see is that this region, I mean this point here, it's where two facets meet, right? It's where the orange facet and the red facet meet, and therefore most of the points in this picture, in this sort of zoomed in picture, will look. Well, most of the tiles here will look either orange or red, orange to the left and red to the right. You will see, however, a few green tiles, the vertical tiles, and it's not so hard to convince yourself that these form an interlacing array, in the sense that for any green tile, there's one adjacent green tile to the left of it and one adjacent green tile to the right of it. For example, in the bottom one, there's one adjacent green tile here and one adjacent green tile here. So we'll denote the positions of these tiles on level k, so on the kth row, by x1, x1 upper k, x2k, all the way to xkk. So I hope this figure makes it clear how I'm indexing these positions. And the tangency statistics question asks, what is the joint law of these xik positions? So again, I'll state the result for a special domain. In this case, it will be the hexagon, which computes the result explicitly. So the statement is if I take the regular hexagon of side length n, then there exists explicit constants mu and sigma, such that the first thing I have to do is I have to take these positions xik, and I have to subtract away something linear in n. So I subtract away mu n. And then I divide out, I scale diffusively, so I divide out by the square root of n. And then the statement is that this converges to a limit, which I've denoted by the CIK here. And this CIK is given by the so-called GUE corners process, the Gaussian unitary ensemble corners process, which is an object it's an object in it's a genuine object in random matrix theory. So to define it, one starts with an infinite array X of standard complex independent Gaussian random variables, and then one defines this matrix M by adding X to its conjugate transpose and dividing by 2. So this will give you an infinite Hermitian random matrix, and then you let Mk denote the k by k matrix obtained by the top k by k left corner of M. So I've just drawn a few examples over here where you see this single entry would be M1, this 2 by 2 matrix would be M2, etc. And then we'll let C1k, C2k, all the way to Ckk denote the eigenvalues of Mk. So these are all coupled objects, and the statement, and then these describe the locations of these vertical tiles in this GUE corners that appear in the limit here. So just a quick comment is that basic linear algebra will tell you that these CIK interlace just as the XIK did. Okay, so the previous result was for the hexagon, as I said before. I want to quickly explain the universality statement that says what happens on more general domains. So we'll fix some domain R with 3 adjacent segments that are inclined to each other at 120-degree angles, as shown here. So you have 3 sides that are inclined at 120-degree angles, but then away from these 3 sides, the domain can do whatever it wants. Okay, it can be completely arbitrary outside of it. Okay, we'll let R denote some tellable domain that's obtained by just scaling this macroscopic domain up by n, and we'll let Mn again be uniformly random tiling of this tellable domain Rn, and we'll denote the x coordinates as I did before of the vertical tiles around this middle horizontal segment by xik, and the statement is that there exists, again, constants mu and sigma that only depend on the domain, such that if I take these xiks, I subtract away by this linear quantity and then diffusively scale, I get the GUE corners process. So this result was predicted by Johansson and Nordenstam in 2006, and the one comment you might have is that I'm sort of imposing. I certainly need, as I said, it's a tangency point. This GUE corners process occurs at a location where this Arctic boundary is tangent to a side of the domain. So I certainly need one straight side, and you might comment, why are you imposing that you have these sides be straight as well? And I should just say that if you expect to see the corners process, then there's a certain sense in which you sort of force 3 adjacent segments to be inclined at a 120-degree angle. So in particular, if the domain has sort of these microscopic dents, as shown to the right over here, where you have a little dent in the domain that doesn't make it exactly straight, you won't see the GUE corners process anymore. So that's why we imposed that constraint. It's in a certain sense, there's a certain sense in which it's necessary. Okay, so that concerns the what happens near a tangency location where you see these GUE corners processes. And I want to conclude. I just want to the last point I want to mention before just having 2 quick slides on the arguments is the proofs is what happens near a facet edge. So we'll fix a smooth point on the Arctic boundary. So on the circle, again, I didn't draw the circle, but you can imagine the circle being inscribed. Again, I'll take a special domain to start with, which is the hexagon. And we'll consider a point on this Arctic boundary, and we'll look at a neighborhood at this point. And then in this case, the correct scaling will be the so-called Carter-Pushy-Zhang or KPZ scaling. So we'll consider an order n to the 1/3 by order n to the 2/3 scaling around this point. And the correct thing to do is to take you take this rectangle to be of order to have length n to the 2/3 in the direction parallel to the Arctic boundary, so parallel to the tangency location, and then order n to the 1/3 in the direction orthogonal to the Arctic boundary, so pointing radially out. So technically, this rectangle should actually be rotated a little bit. The one I took should actually be slightly rotated. But yeah, okay. So this is the scaling one takes, and one observes what happens in this local neighborhood at the edge of the facet. So here I'm taking in this picture here, I'm looking at a green facet here. So the majority of the tiles in this neighborhood are all green, except you will see a few, since you're looking at the edge of the facet, where the facet stops becoming a facet, you'll see a few tiles of the other types. And you'll see a few orange and red tiles. And these orange and red tiles, if I erase all the green tiles, they'll form a family of paths. So in this picture here, I've erased all of the green tiles, and as you can see, they'll form a family of non-intersecting paths, which I will denote by x1, x2, etc. And you can view xi as being indexed by a vertical coordinate, a time coordinate t. So I can look on, say, the fourth, on the fourth layer, t equals 4, and then I will have x1, 4, x2, 4, all the way up to, etc. So the extreme path, the leftmost path, x1, is exactly the interface between the frozen region and the liquid region, where the frozen region stops becoming frozen. And the edge statistics question is, what is the joint scaling limit of these paths? Again, on the hexagon, it was shown by Kreischer, Bauer, McLaughlin, and Miller, and a stronger version of it by Petrov. The full version of it by Petrov is that on a hexagon of side length n, these random paths, they'll converge under a suitable scaling to what's known as the area line ensemble. So let me first just mention the scaling. So these A, B, and C, these parameters A, B, and C, they're all just constants more or less that I won't write down for you. I take my paths and I look in the lateral direction by n to the 2/3 more or less. So I'm looking at a coordinate on these paths that's scaling like n to the 2/3 times some number t. This thing I have to subtract away to see the fluctuations of this thing. I have to subtract away by n to the 2/3, and then the fluctuations will be of order n to the 1/3. So I divide out by that, and then what I'll see in the limit is a bunch of curves now. I'm scaling down a bunch of paths, and what we'll get in the limit is a bunch of curves, which are denoted by these AIT, and then you actually have to shift them up by t squared. So this family AIT, it's A1T, A2T, etc. It's often referred to as the area line ensemble. So it's a family of continuous, random, non-intersecting curves, A1T, A2T, etc. So an example is shown over here, where you see this family of curves. A1 is on the top, A2 is on the second, A3, etc. So these go down. And this line ensemble is very prevalent in this KPZ universality class that consists of a lot of growth models. The top curve, for example, is known as the RA2 process. It's ubiquitous in various types of growth models, such as exclusion processes or last passage percolation, or conjecturally, the Eden model. So it's a fairly universal object. It can be described explicitly as a determinable point process with an explicit kernel. In particular, this kernel is sometimes known as the extended area kernel. And again, the connection to random matrix theory is that this area line ensemble appears in the edge limit of Dyson-Brownian motions. So namely, if I consider the law of the largest eigenvalues, the limit process of the largest eigenvalues of a large Hermitian random matrix whose entries are evolving according to complex Brownian motions, this is what you'll see in the limit, this area line ensemble. So I want to now state the universality result in this context. So we'll fix some polygon P whose sides are parallel to the axes. So of T, satisfying certain technical restrictions. And for the experts, I will just quickly mention these technical restrictions in a second. We'll fix some regular point P on the Arctic boundary of this domain of this domain. We'll define a polygon, which is just obtained by scaling up this domain, this polygonal domain, and we'll let V denote some vertex that's obtained by scaling up this continuum V, so some vertex in this polygonal domain, and we'll let M be a random tiling of P, and we'll consider the family of discrete random walks around this vertex V that's near the facet. And the statement, which is hopefully seen up here, is that under the same kind of normalization as above for these general polygonal domains, under this n to the 1/3, n to the 2/3 normalization, this family of random walks converges to the area line ensemble. So just a quick mention on these technical conditions for the experts. There are conditions on the Arctic boundary of the domain. So for those who know this theory, you will know that the Arctic boundary has certain singularities, and this condition is basically on how these singularities look. Namely, they have no tack nodes. There are no tack node singularities, no cuspidal turning points, and no two distinct cusps are on the same horizontal level. Now, I should just mention quickly about these conditions. They all impose algebraic constraints on the side lengths of the domain. So I mean, so one expects for, say, generic side lengths that don't have any algebraic relations between them, that this condition holds. So, I mean, one expects this condition to hold for polygons with generic side lengths. So, yeah. Okay, I just want to quickly mention a few points on the proofs before concluding. So, so previously, the main tool that had been used was an observation that dates back to Castellan almost 60 years ago by this point, which are that random tilings are determinant of point processes. So correlation functions of random tilings are given by minors of a certain matrix, which is known as the inverse Castellan matrix. So now the problem is that, okay, these correlation functions are determinants of this matrix, but that still means you actually have to compute the matrix. And that's somewhat difficult. If you want to compute this matrix on arbitrary domains, that remains a challenge. There's been some progress or some interesting ideas in this direction over the past several years, but this still remains a deep open question for fairly general domains. Although on specific families of solvable domains, it is known how to compute this inverse Castellan matrix explicitly, and it's given so some families of domains in which you can compute it include the torus, certain families of weighted plane partitions, hexagons, trapezoids, and a certain family of infinite trapezoids, which I won't go into too much detail about them here. So for this reason, previous sorts of asymptotic results concerning these local statistics, what you often had to do was you had to find a family of domains in which you can compute this inverse Castellan matrix and then analyze it. So for that reason, previous limiting results often just address one family of domains at a time. So to prove the universality statements of the generality as mentioned in the previous slides, what we'll instead do is we'll locally couple the tiling on a general domain to one on a solvable one. So this will consist in 3 steps, which you can sort of view as an analytic, an algebraic, and a probabilistic step. So the analytic step is basically improving, and this is going to be somewhat vague. I mean, this is a qualitative outline. Consists in proving an a priori estimate on the tiling of some general domain. So you take your general domain, which is maybe harder to analyze, and you prove some estimate about it. So one example of such an estimate might be a concentration estimate for the height function. Okay, so then the algebraic step is to locate a family of solvable domains, for which you can prove that these universal limiting statistics appear. So I've listed several examples of such domains on the previous slide. And then the third step, the probabilistic step, is to use the a priori estimate from the first step to locally couple the tiling on this original general domain to one on a solvable one. So again, this is somewhat vague, but just to give you an example of how this might look, you might imagine you have your tiling on the general domain, and you use this sort of a priori estimate, say the concentration estimate, to sandwich the tiling between 2 solvable domains. To bound it above and below on 2 solvable domains. So if you can say that the 2 solvable domains are somewhat close to each other, you'll be able to couple the tiling between these 2 solvable domains which are close to each other. So again, this is somewhat vague, but and the implementation of this sort of qualitative process that you would use in order to prove these universalities, these local statistics, proceeds very differently depending on which point you zoom around. So just to mention, for these tangency locations where you see the GUI corners process, the analytic estimate that you need is a subdiffusive concentration estimate. So just anything better than order n to the 1/2, where n is the diameter of the domain. And the family of solvable domains, the algebraic step, which you will eventually couple your model to, is a trapezoidal domain. For the edge of the facet, you need a much better concentration estimate. You need a concentration estimate in order n to the delta for any positive delta. Actually, I think anything better than n to the 1/3 should suffice. And the family of solvable domains to which you eventually compare is the family of hexagons. And in the bulk of the liquid region, the estimate that you need is the so-called local law of large numbers. These are this type of estimate basically says that the limit shape, the law of large numbers, appears on very local scales. So this has gained a lot of popularity in recent years due to the fact that it was one of the main inputs needed in a lot of the recent progress in random matrix theory by the Ardeshline-Yau group in the past decade. And one has to prove a similar estimate in the context of these random lozenge tellings, which is proven through very, very different methods. But the phenomenon is still true in the sense that one still has some sort of local law. And the family of solvable domains is is a family of infinite domains given by certain infinite trapezoids. Okay, so just to summarize, I should say that loss and challenge are very sensitive to their boundary conditions, and the local statistics are very sensitive to the boundary conditions. They're different depending on where one looks inside the domain. So in the bulk of the liquid region, one sees these ergodic translation invariant Gibbs measures given explicitly by these incomplete Bessel process of this discrete sign kernel. At the Tangency location, one sees these GUE quarters processes, and at the edge of the facet, one sees these area processes or area line ensembles. And previous results show that these statistics held on specific families of solvable domains. And these more recent results established universality phenomena, namely that they appear generally on a fairly wide and general class of domains. And the proofs are based on a combination of algebraic and analytic and probabilistic tools. The analytic part is by proving a coarse estimate on a general domain. The algebraic part is proving some refined asymptotic statistic statement on a specific domain, and the probabilistic is the glue that allows you to couple the two models and conclude what you originally only just shown a specific domain holds on these general domains. So with that, thanks for your attention, and yeah.
Thank you very much for this beautiful talk. Any question, comments? Yeah, up there.
Hi, thanks for the nice presentation. Did you study what happens if you do some coarse graining?
What do you mean by that?
Like you choose a bigger lozenge bigger lozenge, and you combine based on some rule of those inside. You decide what type of lozenge it is.
Wait,
in the context of renormalization.
Oh yeah. Okay. So I mean, yeah. So what one might do is you take some big domain, and then you take a bigger domain, and a bigger domain is. Yeah. So this type of multi-scale analysis is not so distant from what I'm talking about. In fact, to prove this local law of large numbers, to prove these analytic estimates, one often needs such tools of this type. But you can only get from at least from my attempts. You can only get estimates using that sort of multi-scale, this renormalization approach. If you want to actually get refined statistics, the renormalization actually won't see it, especially in these locals. I mean, for example, in the local statistics, you're only seeing discrete lozenges, and therefore, if you sort of zoom out, these lozenges are going to become invisible. But this sort of renormalization idea is quite useful for proving bounds that will eventually be used in the sort of analytic step.
Any other question? Yeah, there.
So thank you for a nice talk. You've shown us those local laws in different types of neighborhoods or different type of points. Is there any relation between the corresponding constants in different regions? Like, for instance, you've got some S and T, right, in the liquid region, and then in this, I forgot the tangent point, you have also a couple of constants. They're absolutely unrelated, or are there some restrictions?
Yeah. Okay, so the S and the T, okay, so there are two ways one might interpret the question. The first is that can the S and the T be arbitrary? And the answer to that is yes. But then you might ask, how does one determine these constants? And these constants are determined from the limit shape. So for example, these A, B, and C over here, they're determined by the curvature of the Arctic boundary at the point you're looking at. So from that perspective, these A, B, and C might have some relations. They're determined by the curvature. Yeah, I'm not, so hopefully I gave some answer to the question. So they can often be, these scaling parameters can often be somewhat generic, but they're determined by fairly specific properties of the limit shape, which are computable.
I more like had in mind like the laws in the liquid zone and in the tangent. Are they absolutely uncorrelated, or there are restrictions? If you have, suppose I know a law in the liquid zone, would it impose some restrictions on the constants which appear in other zones, or not at all?
Okay, well. Sorry, let me go back a little bit. Okay, so knowing the constants in this green box will tell you nothing about the constants in this blue box. But knowing if I take this green box closer and closer to the blue box, I will be able to fish out what those constants are. So yeah, if I take if I take two arbitrary points, then the constants will have nothing to do with each other. But if I sort of try to take that green box closer and closer to the blue box, I should be able to fish them out.
Okay, thank you.
Yeah.
Any other question?
There is an online question. I can ask it from here. So the question is as follows. So the representation via vertical dominoes seems fundamental for the argument. Can this be extended to more general graphs, for example, isoradial ones or other non-uniform tilings?
Oh yeah. So okay. So the one answer I should say off the top of my head is that it should extend to domino tilings. So at least in that case, you don't have. I mean, the vertical tile plays less of a special role. So I mean, I mainly emphasize the vertical tile for just descriptive purposes because they're very visually easy to see. They're not super important if one tries to see these local statistics. I mean, it's not super fundamental to have a vertical tile. So this, I mean, I expect similar arguments to apply to say domino tilings. I have not sort of tried to expand the family of lattices to the most general ones. I actually don't know to what extent. I mean, I can't say a priori or offhand to what extent these results are extendable to dynamo models on completely general isoradial or doubly periodic or graphs.
Thanks a lot. There was somebody got a question over there. Yeah.
You mentioned at the beginning that it's an open conjecture that the fluctuations around the limit shape converge to Gaussian free field. Is that result totally outside reach, or does your work offer some perspective on making some progress in that direction?
Okay, yeah. So I didn't personally think too much about the Gaussian free field. I was more interested in these local questions in this work. However, what this does show is that the height function delocalizes. I mean, which is what you would expect in the Gaussian free field. Now, I know that there's been some progress in sort of showing a dichotomy between, I mean, especially among the experts in percolation, and showing that there's a dichotomy between logarithmic fluctuations of the height function and gaseous regions, which are localization of the height function. Like the height function is localized or it's delocalized, and it satisfies. And it has logarithmic fluctuations. So what some of these results imply is that the height function is delocalized. So if that technology can be applied in this dimer context, then that might be useful to show that you at least see that the fluctuations are logarithmic. But that's all I can say in that direction.
Thanks a lot. Jörg?
Are there any substances that I could explore in a laboratory that can be described by some of these models?
Yeah, so I think I would expect, for example, a melting crystal should be explainable by this model. So see, I don't have the picture that makes this convincing. Yeah, I don't have the picture that makes this convincing, unfortunately. But yeah, so I mean, basically, you can imagine. I think ice is probably not the correct one, but you take a crystal in a cubic shape, for example, and you start melting the corner of the crystal. And then what you will see is something that looks very similar to the Lossenstellung of a hexagon. Yeah, and if you take maybe more exotic, you don't start with the crystal, but you take some more exotic, some sort of more exotic shape of the substance to start melting it, you will start seeing the Lossenstellung, these sorts of cubes on these appearing on these more general domains.
Okay, thanks a lot. Any other question? Let me just ask one last question. If you compare these three proofs which you presented, the three results, what is the comparison in terms of difficulty? Which one is the most complicated, least complicated?
Oh, this is a very loaded question. I think, at least, so I've find them. Well, at least, okay, so one thing I can say is that probably the hardest part in each of these steps is proving the analytic estimate. So at least if I wanted to say that. I would say among the easiest is probably the tangency points. That's, I mean, at least the arguments are shortest there. Between the bulk and the liquid region, sorry, the bulk and the edge, I think they're too different for me to the arguments for proving the estimate are too different for me to be able to compare them in a straightforward way. But I mean, yeah, they're just completely different arguments. But I mean, I might say that the tangency is at least the shortest, by far the shortest proof among these.
Okay, thanks very much. If there is no other question, then I thank the speaker again.
Thank you.